the presentation is today is simulation at the pace of design. And we're going to be focusing on one specific simulation software in our portfolio that is quite revolutionary in the sense that it allows you to do simulation iterations at the same time as sort of the design is being constantly enhanced and refined. Something we believe is a complete new paradigm in simulation. The idea of doing simulation has been around for decades, but it's traditionally a quite cumbersome process that you need to build your simulation models thoroughly, and you have to do things like simplifying geometry, meshing, setting up loads of boundary conditions, and all that takes quite a bit of time. And in order to just build a complete simulation model of a car or an airplane or something, that's typically a couple of weeks of work that goes in. So until you can actually draw some conclusions, you have to spend quite a bit of time just building the simulation model. But SimSolid, which is the tool we are introducing today, that's also a structural simulation tool. But in contrast to a traditional finite element-based tools, we're operating directly on the original unsimplified CAD. And the CAD can be single parts, but it can also be huge assemblies with hundreds or even thousands of parts. And what we do is that we do not create a mesh, but instead we apply the numerical equations directly based on the geometric definitions in the CAD. So it's very much taking away a lot of the burden of doing the modeling to be able to do simulation. And in addition to that, because we do it in a very clever way, we're able to solve the actual equations really quickly. So even for large-scale assemblies, you can get results in seconds or sometimes minutes, even if you run on your local laptop. So it doesn't rely on a big sort of expensive simulation cluster or HPC. So just speaking a bit about the modeling part of things. So if you think about traditional finite element models, there are a lot of challenges that has to be overcome in what is called a pre-processing. So the process taking you basically from a CAD to a ready-to-run simulation model. And that includes things like having assemblies with big differences in scale in terms of thicknesses and size. And so you might have some really small part and some big parts, and you have to adjust your mesh settings to cope with that. You oftentimes have small geometrical features that doesn't necessarily have a big impact on the simulation results, but they have a big impact on what sort of mesh quality, etc., that you can achieve. So oftentimes you have to spend time on simplifying geometry and removing small holes or fillets and doing idealizations. Sometimes the geometry is extremely complex. So you may have to spend tons of time just trying to fit a mesh onto that geometry definition. And we've all seen these cases where you have small sliver faces and stuff in the CAD that messes up the mesh because you're getting tiny small elements that needs to be repaired and fixed. And none the least, especially in the early stages of product development, the CAD is never perfect. There are gaps and overlaps and intersections that needs to be taken care of in order for a simulation software to be able to solve it. With SimSolid, none of these issues actually are issues, because of the formulation where we use the real unsimplified geometry as is. So a lot of the time saving using this tool is from the modeling side of things, as you will be seeing later on in some real world examples as well. So just saying a few words about the capabilities of the tool. So in terms of the types of solution sequences it supports, of course, it does all the sort of basic stuff like linear static analysis, modal analysis, and so forth, but it doesn't end there. It's also capable of doing nonlinear simulations, doing thermal simulations and linear dynamics simulation. So it's a quite broad range of different solution sequences that are being supported. Also on the material modeling side of things, of course, it's doing isotropic materials, and there's a comprehensive material library with different predefined materials. But it's not just doing sort of isotropic and not even, it's obviously doing nonlinear materials like elastoplastic materials and so forth, but also orthotropic materials. Like if you have a composite material which has different properties in different directions, SimSolid is able to cope with that. And you can define your own models or material models. So if you have test data like stress strain curves and so forth, that can be inputted and you can use your own materials in the simulation. Another thing that takes a lot of time in traditional finite element modeling is to define the connections in between different parts and different subsystems. That can be things like bolted joints, it can be spot welds or laser welds or seam welds or bushings or rivets or joints and stuff like that. And that capability in SimSolid is to a large extent outstanding, I would say, in terms of generating all this contact in an automatic or semi-automatic way. There's a lot of time to be saved by using SimSolid instead of a traditional finite element tool. A bit about the type of results you would get. So the results you get doesn't really differ anything from the type of results you get from a traditional finite element analysis. You would get all your different contour plots like displacement, stresses, strains, acceleration, whatever you're interested in. And you can obviously find your maximum results, your minimum, and see all things graphically. Then, of course, you can look on things like reaction forces or volt forces, different types of strain energy and whatever sort of curve data you're interested in. And if you're doing thermal analysis, of course, you can plot temperatures and all sort of things. So I hope this gives you an idea about the general capabilities of the tool.